So we are very fortunate to have Varsha Kishore with us here today. She is a PhD student from Cornell and is interested in evaluation metrics, retrieval-based generation, and text diffusion. And we're excited to have her talk to us today. Take it away, Varsha.
Thank you for the introduction. I'm excited to be here and present some of my work today. Let me share screen. Okay, my screen is visible?
Yes.
Okay, thank you. All right. I can't see any of you because I'm sharing my screen, but please feel free to interrupt me with any point with questions. I'll also pause after sections to see if there are any questions. Okay. So today we have textual data available in a bunch of different formats. We have news articles, we have Wikipedia articles, papers, code, etc. In the last few years, we've seen different architectures being developed for learning about this data and performing downstream tasks with these models. I am particularly interested in examining latent spaces of language models. I want to understand how information is stored in them, where information is stored, and whether you can use insights from understanding these spaces to develop specific methods for tasks. In this talk, I will be talking about 3 of my projects. The first one will be about using contextual embeddings to evaluate similarity between any 2 pieces of text. In the second project, I'll be talking about learning a document embedding in the context of an end-to-end document retrieval system. And finally, I'll tell you a little bit about our recent work on using classifiers in some nice latent space to guide generation from language models. Yeah. So I'm going to start with BERTScore. BERTScore was my first project after I started my PhD. So this was in 2018. This was about the time when transformers were introduced, BERT specifically. One thing people noticed at this time was that BERT is very good at learning contextual representations for words. So these embeddings captured semantic, syntactic, and contextual information for every single word in the sentence. This meant if you have the same word in the sentence appear at different points, the representations would be different to account for the context in which they appear. You would also have different representations if the same word had different meanings. For instance, if you look at the word park, it could be you could be talking about parking a car, or you could be talking about going to a park where, and you would want these to have different representations. Okay. So while I was looking at this BERT model, I was also simultaneously reading literature, trying to understand what I wanted to work on, what the state of the art was, and such. So one thing I noticed was a lot of papers needed evaluation metrics. This makes sense. If you develop a method, you want to know how good your method is. In the context of machine translation, you could have a source sentence. Here you have a German sentence. We produce a translation of the German sentence, and this is the candidate on the slide. We also have a ground truth for what a human would translate this sentence as. So a similarity metric would basically quantify how similar your generation is to some ground truth reference. In 2018, the common approaches for evaluating textual similarity fell into 3 different categories. The first one was n-gram matching, and these were the most common. So these were metrics like BLUE or Meteor or Rouge. And essentially, these metrics look at different n-grams between a candidate and reference sentence and try to match them. Although they worked to some extent, they had a few limitations. They were not great at matching paraphrases. They were also very sensitive to changing word order or small changes in the sentences. Next, we have embedding or parse-based metrics. These often involve multiple subsystems, and it wasn't easy to set them up and use them in practice. Finally, we had learn metrics like RUSE. Here, people used data sets of pairs of sentences and their corresponding similarity score, and directly train neural networks to predict a score given a pair of sentences. Although learned metrics work quite well in domain, even a slight shift in domain makes it such that these metrics no longer give you good results on computing text similarity. Okay, so we looked at BERT and we looked at this problem of evaluating text similarity and said, can we use embeddings from BERT to do better? So we have a candidate sentence and we have a reference sentence. Both of these can be embedded with a BERT model to obtain word embeddings for the sentences. In an embedding space, they would look something like this. So here on the left, we have the candidate sentence, and on the right, we have the reference sentence. And the task is to measure some notion of how hard it is to transform the sentence on the left to the sentence on the right. So we looked at a few different ways of computing this cost of transforming one sentence to the other. And one natural metric to use was the word mover's distance. The word mover's distance is also known as the earth mover's distance or the Wasserstein metric in different contexts. But essentially what word mover's distance is trying to do is minimize this optimization problem. And this optimization problem, we see that we have two terms. We have Tij and Dij. Tij is measuring how much of each word in your candidate, how much each word in your candidate sentence is being transformed to a word in the reference sentence. The distance is telling you how hard it is to transform word I to word j. So if you have dissimilar words, the distance will be higher, and so the cost will be higher. So if you look at this optimization problem, it's trivially satisfied if you set all the Tijs to 0. But this is not what you want, right? You want to be transforming the words and not just, if you set Tij to 0, that means you're transforming nothing. So we have a few constraints. This first constraint is saying, if you look at any word in your candidate sentence, it has 1 over n units of information, where n is the number of words in the candidate. So the information flowing out of each word in your candidate sentence should be 1 over n. The second constraint says that the information coming into any of your reference words should be 1 over m, where m is the words in the reference. So this works well, but this is computationally very expensive to compute. More specifically, its complexity is cubic in the number of words. And if we have an evaluation metric, we want it to be quick and easy for people to use. So in order to simplify this, we looked at what would happen if we dropped one of these constraints. So now we remove the constraint that says 1 over m amount of information should come into each reference word. If we do this, our problem reduces to greedy matching. So now the best solution is for each word in your candidate reference, greedily match it to a word in the reference. Okay. So how do we do this in practice? Essentially, all you need to do is compute a similarity matrix between your word embeddings from the candidate sentence and the word embeddings from the reference sentence. Once you have a 2D matrix, you can compute matching between the candidate words to the reference words and vice versa. So if you're matching candidate words to the reference, you're computing precision. And if you're matching reference words to the candidate, then you're computing recall. Okay, so we're going to look at the first word in both the candidate and reference. And we're going to match either row-wise or column-wise, depending on whether we're computing precision or recall. To match it, we find the maximum score. You can do this for every single word in both your sentences. Once we have these maximum scores, they can be aggregated by averaging. So we have a precision score and a recall score, and both this precision score and recall score can be combined to compute an F1 metric. Okay. So we have a method for scoring two sentences. Now we want to evaluate this. So to evaluate this, we use the WMT translation benchmark. In this data set, you have reference candidate sentence pairs, and each pair has a human score for how similar the reference and candidate are. We can also score these pairs using our metric BERTScore. And finally, we want to compute a correlation between the human scores and the scores given by our metric. Ideally, we want this correlation to be high because we want the scores we output to be close to that of human judgment. So one thing I didn't quite specify was how we're getting these embeddings from the BERT model. You could get embeddings at the last layer after running your input through a BERT model, or you could also get embeddings from intermediate layers. And turns out empirically, using embeddings from not the last layer, but a layer close to the last layer works well. A few other papers have made similar observations. My best guess for why this would be true is I think towards in the last layer or close to the last layer, BERT embeddings sort of overfit to this masked language modeling task, and using representations from a few layers earlier are better for generalizing and learning contextual information. So here are results of using BERTScore versus some other baselines. These are results for different translation tasks. For the ones that are that have English as the source and a different language as the target, we use a multilingual model, but the same method. As you can see on this plot, BERTScore does outperform baselines for computing correlation. But apart from these quantitative results, BERTScore has also been widely used for a whole bunch of tasks since we introduced it. And these are tasks like question answering, dialogue systems, prefix tuning, summarization, etc. For a lot of these methods, BERTScore is just used for evaluation. But for some others, BERTScore is actually used as a subroutine in developing their method. Another common evaluation metric that people use, BlueWord, is one such method that uses BERTScore as a subroutine. There are also hallucination reduction methods that use BERTScore to grade factuality of sentences and generate factual outputs. Okay, I'm going to pause here if there are any questions. Great. So far we talked about computing similarity between two pieces of text, and usually these are short pieces of text. Now I'm going to transition and talk about computing similarity between a given query, which is usually a short piece of text, and a document, which is much longer. I'm going to do this in the context of document retrieval. So for document retrieval, the task at hand is to find a relevant document for a given user query. So user issues a query. We have a database of documents. We want to find a document that is relevant to the query and produce that document. Usually for document retrieval, you have some number of documents. Each of these documents can have multiple queries associated with the document. So you have a set of queries and a set of documents. The dominant paradigm for doing document retrieval is to use two encoders, a query encoder and a document encoder, to encode both the queries and the documents. This whole system is trained with contrastive loss to ensure that embedded queries are close to their corresponding embedded documents. So if you look at an embedding space, the pink purple dots here are the documents. The green X's are queries. Each query has a corresponding document, and the system is being trained to ensure that the query moves closer to its corresponding document. Okay, so once you have a trained dual encoder system, you freeze both your document and your query encoder. All of the documents in your corpus can be encoded with this document encoder. This is now saved. These embeddings are saved in a database. And then whenever a user issues a query, you embed the query through the query encoder and compute a nearest neighbor search to retrieve a relevant document. So if you notice, this system has two steps, an indexing step and a retrieval step. So this worked quite well. But in 2022, a few researchers at Google introduced an end-to-end document retrieval system that was trying to combine both this indexing and retrieving step and develop one method that could directly map queries and documents to their corresponding document IDs. So if you notice in this diagram here, we have a single retrieval model. This is usually some sort of a transformer-based model. This model can take as input queries or documents, and it directly produces a document ID. Usually, this is set up as a classification task. And the number of classes is very large here, right? So if you have 100,000 documents, this is a 100,000 way classification. So one thing you might notice right off the bat is in comparison with the dual encoder methods, you never have access to the embeddings directly. Information about the documents is stored somewhere within this retrieval model. And then this whole system can be trained end to end, and it results in better performance compared to the dual encoder models. One subtlety is for the next few slides, I'm going to treat queries and documents interchangeably. Because in this system, they are treated equivalently. It doesn't matter if it's a query or a document. And often for DSI type systems, these documents are discarded. Instead, you generate queries from the documents and use the generated queries to represent documents. But for the purposes of this talk, you can think about these inputs as either queries or documents. Okay. So yes, these DSI systems work better than dual encoder systems in terms of performance, but they also have a few limitations. One of the most important limitations is it's not clear how to add new documents in this DSI system. So if you had a dual encoder, given a new document, you could embed it with your frozen document encoder and add that to your database of document embeddings. However, in this DSI system, if you had a new document, you would have to add a new class to your classification layer. And without being trained additionally, the model would never generate the new class that you just added because it was not trained to generate that class. And adding new documents is an important problem, right? So in most settings, you have a corpus of news articles or a corpus of scientific papers. And these are growing corpora. Usually you want to be able to adapt your retrieval system to new documents that might become available. Okay, so it's not clear how we go about adding information to this retrieval model. So we look deeper and we try to figure out what is happening within this retrieval model. Once you examine the model, it turns out you have a transformer encoder and you have a linear layer. The system can be separated in this way. And this linear layer is producing an output. This linear layer is essentially doing a classification task, right? So each column in this linear layer can be viewed as a document representation. So the first column here might correspond to a representation of document 142 and so on. So given a query, at the end of the transformer encoder, you have this green vector here. So this is some embedding of the query. And you have the gray matrix, which is the classification layer. So to do classification, essentially, you're computing a nearest neighbor search between this green vector and the gray matrix. Once we made this observation, we can phrase the problem of adding a new document as learning this new purple vector. So if Gemma is the new language model that was just introduced and you want to add information about this model Gemma into your trained document retrieval system, we're going to be learning this one additional purple vector that will be added to the classification layer. So an important thing to note here is the rest of the model is frozen, the transformer is frozen, and the rest of the classification layer is frozen. So all we are trying to optimize is this one purple vector. So if we look at this embedding space again, where we have our documents encoded, we can encode new queries. These can be user queries, or these can be generated from the new document that you're trying to add. So the queries are shown in purple. The queries are embedded with the encoder. Now you have a randomly initialized point for this new purple vector that you're trying to add to your classification layer. And ideally, we want to move this closer to the relevant queries. Okay. So how do we do this optimization problem? Before I tell you that, this is some notation that I'll use. I'm going to denote the classification layer as V. The new document vector that we are learning is going to be vn+1. So we are assuming we had n old documents, and we have one additional document that we're going to add. And the document vector corresponding to the new document is vn+1. We also have a set of old queries corresponding to documents that were already in this model. We're going to denote those queries z bar. And we have some new queries corresponding to the new Gemma document that we're just trying to add. So we're going to denote the new queries q bar. So our task is to find this new vector vn+1. So we have two sets of constraints to find this vector. The first set of constraints ensures that the new queries are correctly mapped to the new document. So essentially, this is a linear constraint that looks like this. Here we're saying vn+1 is a vector and qn+1 is a query corresponding to this new document. We want the dot product of qn+1 and vn+1 to be greater than the dot product of qn+1 with any other document vector. So this ensures that the new queries are correctly mapped to the new document. But while we do this, we want to ensure that we still retain performance on the old document set and we don't change anything with the old document set. So our second set of constraints ensures that the old queries are still correctly mapped to their corresponding old documents. So this is a similar linear constraint where we're saying if you take an old query z and compute its dot product with vn+1, we want it to be less than the dot product with the corresponding document embedding that zj is from. Okay. We minimize the norm, the two norm of vn+1 to make this a nice convex optimization problem. It also acts as a regularizer and ensures that we learn a reasonable vector vn+1. So this is a convex optimization problem. You can solve it using a convex solver, but we found that it's much faster actually to translate this as a loss function, where we're trying to minimize the two norm of vn+1. And each of these constraints can be written as violations and added as terms to the loss function. We then solve this optimization problem using LBFGS. Our method is called IncDSI. And we show that with IncDSI, we can add new documents in 20 to 50 milliseconds. This is quite fast. On this graph here, we see IncDSI in purple, but we also see DSI DPR and DSI Scratch in green and blue. So both these green and blue bars are baselines where you're retraining your whole method from scratch or continually training with your old and new data. This is quite expensive to do, right? You can't just train on your new data because you forget your old data. So you have to train on both your old and new data. In this graph, the numbers on top of the bar are accuracies. So the important thing to note about accuracy is we recover the same performance as retraining from scratch with the old and new documents. But the nice part about IncDSI is this is way faster. If you're just trying to add one document to your system, you don't want to retrain the whole method for multiple hours. You want to be able to quickly add these documents. And this plot is showing that we can indeed add documents quickly with IncDSI. All right. Any questions before I go ahead? Okay. I'm going to switch gears a little bit and talk about controllable language generation now. We'll see how we can use certain latent spaces to guide generation of language models. So I've intentionally abstracted some of the math and details out of this part of the talk. If anything is unclear, please stop me. Or if you're interested in any of the math, ask me. I have skip slides that I can use to provide context. Okay, so controllable generation is the task of guiding generation. You might want to do this because there might be attributes you're interested in. You might want to generate things in a certain style or with some amount of formality or specific to some topic. You could prompt a language model to do this, but you might also want more explicit control for guiding generation. One thing you could do is you can use RLHF, but if you use RLHF, many papers have shown that it sometimes degrades performance of unrelated other tasks, of performing other tasks with the same language model. So often what people do is use plug-and-play methods. So in the plug-and-play setup, the autoregressive decoder is frozen. So this could be a GPT model or so that's frozen. What you do then is you train external classifiers and use signal from these classifiers to guide your generation. Although this works, there is inherent tension between the language modeling objective and the control objective for your guidance. This, in practice, is sometimes brittle. For instance, you might be using guidance to make your generation more positive. And if you do this while completing a sentence, you might end up in a spot where the rest of the continuation is not clear and is of lower quality because you intervene too strongly at a given token. So the question we wanted to ask is, can you use a latent space and provide guidance in some smoother space? To do this, we make use of some prior work on latent diffusion for language generation. So this is work with a collaborator at Cornell. In past work, we learned a diffusion model in the latent space of an autoencoder and showed that this works well for doing conditional generation tasks. So in the current context, we trained a diffusion model in the sentence T5 latent space. What this means is, given a prompt, we want to generate a continuation. The continuation will be embedded in sentence T5 space. So here a prompt could be New York is, and your diffusion network generates a continuation, for instance, it can be New York is, and the continuation is in the eastern part of the United States. And the continuation embedding would correspond to embedding in the eastern part of the United States in the sentence T5 space. So once we have such a diffusion network, we can plug it in to our autoregressive decoder. So let me back up and explain what's happening here. Here you have a prompt. You're also sampling Gaussian noise for your diffusion network. The diffusion network generates a semantic proposal for what the continuation should be. This semantic proposal is fed into the decoder model as a soft prompt. The autoregressive decoder uses both the soft prompt, this soft prompt, and the original prompt to generate a continuation. You might ask, why did we do this? And the reason we did this is because we wanted to learn an embedding space that is smooth and continuous and nicer to interpolate in. So if you remember, we learned this diffusion network in the embedding space of a sentence T5 model. Prior work has shown that attributes like sentiment, toxicity, etc., can be linearly separable in the sentence T5 space. It's quite fast and quite simple to learn a logistic regression classifier in the sentence T5 space for things like toxic versus non-toxic, positive versus negative, or even to distinguish between topics like sports, news, etc. So once we learn a classifier in this embedding space, we can use guidance from that classifier to generate this semantic proposal. So diffusion is inherently iterative. So when you provide guidance in this space, not only is it continuous and smooth, but the semantic proposal can also be iteratively refined before it's given to the autoregressive language model. And then the autoregressive decoder just has to do the normal language modeling task, and there's less tension between these two separate objectives of controlling a generation and performing language modeling. Okay. Here are some results from using diffusion-guided language generation. The pink triangles are our method, diffusion-guided language modeling. The S parameter tells you how strongly you're providing conditioning information on any attribute. In this case, it's toxicity. So we see that as we increase the strength of the guidance, our toxicity decreases. We also see that the perplexity does not increase all that much. This is nice. This means that we're able to control generation without making the quality of the generated text much worse. On the plot on the right, we show diversity. This is just capturing how diverse are the outputs, and we measure this by looking at unique n-grams. There are also different baseline methods shown on these plots. GPT-2 is just using vanilla GPT-2. PPLM uses a classifier in token space and tries to provide feedback. Both JEDI and Dexperts use auxiliary language models or LoRa fine-tuned language models to guide generation. So this is much more expensive than just learning a logistic regression classifier. The last one, DAPT, fine-tunes a model on specific toxicity or sentiment data, and this is also more expensive to do. Okay. So in conclusion, language models learn useful latent spaces, and understanding these latent spaces can help design methods for specific downstream tasks. First, we saw that contextual embeddings from a BERT model or any other encoder model can be used to gauge sentence similarity. Then we saw in the context of document retrieval, you can use optimization to find representations for new documents. Lastly, we find that looking at latent spaces, some spaces are nicer than others to learn classifiers in, and we can use classifiers learned in a diffusion, in a sentence T5 latent space to guide generation from autoregressive language models. All right, I'm gonna stop again for questions before I talk about future work.
Looks
I
like
have
there's
a question.
Yes.
Go ahead.
I was wondering how much can you do diffusion guided generation for multiple guidances simultaneously, and how broad is it? Can I guide it to use tools? Can I guide it to be more factual? What's the limit here?
Yeah, so to answer your first question, you can guide different attributes. So you can have, I want to generate something that's positive, and I want to generate something that's about sports, right? Two different attributes. And actually, the diffusion framework makes it much nicer to compose these attributes. And we have some examples of doing this in our paper, and it works way better than any of the baselines. As for the limit of what things you can guide this model to do, it depends on finding these classifiers in the sentence T5 embedding space. So if you can find a separable direction or train a classifier in the sentence T5 embedding space, then you can use that attribute for generation.
Do you, in general, know how hard it is to find something? So what's the procedure if I come up with some kind of complex idea? Can I find it? If I can't find it, does that mean it doesn't exist? Or what can we say about this?
Yeah, so if you come up with some kind of an attribute you want to control for, you would need a labeled data set for positive or negative instances of this attribute. And then all you need to do is embed samples in embed continuations or prompts in this embedding space and train a logistic regression classifier to find a linear separated boundary. If you don't find such a, if you train a classifier here and you don't get good performance, that probably means the space is not good enough for finding the separation. So you could try using a classifier that's nonlinear and can learn a more complex decision boundary. Or you could also try to find a different embedding space in which you have better directions for the attribute you want to control.
Oh, interesting. Okay, sorry for so many questions, but I have one more.
I appreciate the questions.
If I wanted to fine tune, let's say I went through this procedure and I didn't find a linear boundary or a nonlinear boundary, but I'm convinced that I have this semantically meaningful separation. Can I fine tune T5 so that its embeddings conform to suddenly form a linear separated boundary without losing its all its rest of its abilities, or is that just science fiction?
I think you can fine tune T5 to find this boundary and then do the same thing in this fine tune space. I don't know if you would break. No. I think if you're able to fine tune T5 to find the separating boundary, then the rest of it will work fine.
Right. I just have to make sure I don't lose the ability. Right.
Yeah.
Okay.
Yeah.
Okay. That's cool. Thanks.
Yeah.
Since there's kind of a pause for asking questions, I'll ask one back to back to the first part of the talk. The BERTScore stuff, did you try any experiments with the more expensive cubic time matching?
Yeah, we did. That was our original method, using word movers distance directly. We got very similar results, like they were within 1 point of each other. And we decided to use the similar version so people would adopt it more easily, and it would be actually practical to use. But since we published this paper, there was another paper that used the word movers distance and did the same thing and published it. So I can send you a reference to that paper. But people have tried it. It's just more expensive and less practical to use.
Okay, what's kind of the intuition for why the more expensive algorithm might not help much in terms of accuracy?
Yeah, so the more expensive algorithm, what it allows you to do is match a single word to a single candidate word to multiple reference words, right? You can say half of cold is matched to freezing and half of cold is matched to weather. If we relax the more expensive problem to greedy matching, you're essentially saying the best thing you can do is match cold to the word that it's closest to. In this case, it's freezing. And I think these contextual embeddings are learned in such a way that it doesn't matter. Like the information that you need is distributed across all of these tokens, and you don't necessarily need to match a word to multiple other words.
Got it. Okay, that makes sense. Thank you.
Okay. I'm going to keep going forward. I'm going to talk about some future work that I'm interested in working on. And then if there are more questions, we can address those again. Does that sound good? Okay. All right. So in general, I'm interested in in developing better language models, specifically retrieval augmented language models. So the setting for retrieval augmented language models, or RAG style models, is you have some document corpus. Given a query, you retrieve relevant documents to your query, and then you use a language model to answer the query, and the language model is conditioned on the documents you just retrieved. So I've worked on different parts of this, as you've seen. And there are some directions that I'm interested in further exploring. Specifically on the retrieval side, I talked about using these end-to-end document retrieval methods. Although they work well, so far most of the experiments on such retrieval models have been limited to smaller corpora, so like a few 100,000 instead of millions and billions. This end-to-end document retrieval methods will probably be harder to use on millions and billions of documents because now your classification problem is just much bigger. So I'm interested in scaling these methods and trying to see whether they work on larger corpuses, and if not, what limitations there are and how we can improve them. I'm also interested in using diversity metrics to retrieve top K documents that are dissimilar in some way. So if you have a query and you retrieve the top 10 documents and they all essentially say the same thing in different ways, that's not very useful. So I want to capture this notion of I want different information from these top K documents in some way. On the language modeling side, I am especially interested in reducing hallucinations. So along with some collaborators at Cornell, I worked on a method for reducing hallucinations in abstractive summarization. So our method essentially was looking for heuristics like change in conditional token probability, and using such heuristics to identify hallucinations, and then we had a backtracking method to correct these hallucinations. I want to see whether you can use such a method for question answering, and generally, I want to see if there are other challenges with detecting hallucinations for question answering. While I was working on this hallucination reduction problem, I also noticed that a lot of the factuality metrics that people use currently are very sensitive to things like length of input or small changes in ordering of the text. So I think there's also definitely room for improving these factuality metrics. Finally, I'm interested in model editing. So if you have a retrieval-based system, theoretically, given you should be able to retrieve new documents and use those as context to your language models. However, your language model also stores some amount of information. And if your language model's information is outdated, this could lead to worse predictions. So there have been recent model editing methods that have been proposed. Some of them are Rome, Mammoth, MEN. You might have heard about these. One problem with these methods is they perform surface form edits. So if you edit the fact the new president of the US is X, it doesn't necessarily change who the president's wife is. So I want to develop methods for reasoning about which facts need to be changed, or which information needs to be edited, and finding better ways to make edits such that not only the fact, but all the relevant dependent facts get updated. Okay. So currently in a retrieval augmented language modeling setup, this retrieval model and this language model are trained separately. I think there's also room for investigating architectures that combine these steps. For one, you could train end-to-end, and it might also give you more flexibility to reason about different things in your model. I'm currently working on this, and I tried a few different ways of trying to do this. But the problem is you need some compact, concise way of storing, of learning some vector stores of factual knowledge. If you look at general dual encoder style retrieval systems or so, the embeddings depend not just on the facts, but also the language part of the text. So it's kind of hard to separate the factual knowledge from the language part of it. And I'm interested in developing better methods to learn factual representations of documents and use this end-to-end with a language model. And I think these learning factual representations is on its own also an interesting question and could lead to better downstream performance on many tasks. Okay. So when these RAG style methods were introduced, documents were provided as context to a language model, and the language model generated outputs. But since then, there have been many improvements in improving generation through reasoning. So this can be done in many ways. So one way is this loop on the left, or reasoning traces. So you can think of reasoning traces as a chain of thought reasoning. So if you use chain of thought reasoning, the language model should be able to explicitly reason about different aspects of your query and generate a better answer. You could also use language models with external actions. Like you could use external tools or databases or retrieval models to improve the generation of your language models. React was a recent paper from a few people at Google, I think, that provided this paradigm or framework for using both chain of thought reasoning and tool use like retrieve external calls to certain functions. I think this is an interesting paradigm, and this will help answer complex queries. There are a few limitations with what React proposes so far. So React looks at a very limited set of actions, like 2 to 3, and their actions are very simple. So these are actions like, if you have an n-gram, what are possible continuations to this n-gram in your documents? I think we can develop much better tools or actions in terms of retrieving relevant information, making comparisons, and such. So I want to expand the set of actions. One other thing we find with React is sometimes the reasoning loops get stuck in cycles. This is because the language model is asking the same, is trying to perform the same sort of reasoning over and over again and doesn't realize how to exit from this. So I think we could definitely improve this method. We could improve and build on this method. We could also think about ways to incorporate human feedback. So zooming out a little bit, my goal is to develop methods to answer complex queries with explicit reasoning. So here's an example, right? Here's an example query. You could ask a query along the lines of, what is the best text diffusion model or method? So to answer this query, ideally, this is what I think we should do. We should retrieve relevant papers. We should then find the results section of these papers and find results for how well the methods perform. And then we want to reason about the evaluation setting, right? If we're comparing numbers from different papers, we want to make sure that the methods were evaluated on the same data sets. And even if they were evaluated on the same data sets, they were evaluated on the same splits or so. Other than that, there might also be subtleties. For this specific question, diffusion methods use a varying number of diffusion steps. Some methods also generate multiple samples and then select a best sample from the set of samples. And so if you have subtleties like this, a model should be able to ask, reason, and think about these subtleties. And finally, you want to generate an answer based on what you've found so far. So if different methods are comparable, you can and use the same data sets, you can generate an answer. If not, the language model should say, here are the results from the different papers. It's unclear how to compare and contrast these. And I think Semantic Scholar would be an exciting place to do to pursue this question and build a method for this, because it provides Semantic Scholar would be a great test bed to test this method on and improve and build it. Okay, all of the work I presented was done with collaborators here at Cornell. I will now take any other questions there are. I'm also happy to talk about any of the future work. Or yeah.
We do have some time for questions. Varsha, I don't know if you can see in the mode that you're in, but there was a lot of applause.
Oh, thank you.
In the Google Meet. So people thank you for the talk. Are there other questions?
I have a sort of hypothetical question about future work.
Mhm.
I've been thinking about reasoning traces in terms of whether we can store them, improve them, retrieve them, and learn from them explicitly. In this kind of React framework that you're describing, what are the reasoning traces ephemeral, or where do they actually enter in terms of their utility, and how extensible are they? What are your thoughts on that?
So the reason traces here are usually sort of done in a chain of thought way. So you either have one language model or different agents. Agents are just language models with certain prompts. So this is an iterative framework. The language model first tries to gather information about the query. And once you have the query, the language model, this is all done with prompts. They don't really train anything. Is prompted to ask whether you have enough relevant information to answer the query. If not, the language model is asked to generate what additional clarification would be required.
I see. And these prompts are designed ahead of time. They're not
These
sort
prompts
of
are designed ahead of time, and essentially you're doing in-context learning. So the authors take a few examples, write out what the trace should look like for those examples, put that in the context, and then train this, and then perform zero-shot evaluation on additional examples.
I see. Okay.
I think there is room for using some sort of LoRa fine-tuning or fine-tuning and not just doing prompting. But I guess the easiest first step to do is just prompt these models.
Yep. Thank you.
Thank you for the great talk. I had a quick question, slightly speculative maybe, about the model editing stuff that you're talking about. I'm curious if you think there's scope to do some sort of human in the loop model editing stuff, because like you said, oftentimes if there's a fact that you want to update, it's not that easy to figure out what else there is that you could change. Do you have any thoughts, or do you have ideas that of potentially involving humans in this process and making it more accurate?
Yeah, so you could use a human in the loop, but it's definitely not scalable, because if you ask me which other facts rely on this fact and should change, it would be hard to come up with an exhaustive set of facts that we should edit. That's one, and I think, yeah, but also once a human gives you the facts and say these are the facts you want to edit, it might be interesting to look at how to jointly edit the model such that you change all of these facts. I think the more realistic setting would be to still design an automatic way of figuring out what the dependencies are and which additional facts need to change, and presenting it to a human to cross-check and make sure that it's reasonable, or add or remove things. Yeah.
Yeah, that definitely makes sense. Do you have thoughts about how we could actually find these facts? Like, I know one way could be we could use knowledge bases, but are there other routes?
Yeah, knowledge bases are definitely useful for this. You could also maybe prompt language models in some ways to ask, this is a fact that I want to change. What other things depend on this fact? It's definitely a hard task to figure out what the dependencies are. Or maybe you can do something in the latent space and say, if you change query X, can you sample things around query X that would sort of be sensitive to changing query X? I don't know if you could store the change as like a change in weight somewhere, and if you end up close to that embedding, use the change. Does that make sense?
Yeah, that's an interesting idea.
Yeah.
It's also, I guess, a hard problem to evaluate because recall is so difficult.
Definitely, but I think recently there were at least 2 papers that introduced some sort of benchmark data sets for ripple edits or multi-hop fact editing. So I think they specify a few situations like 2-hop logical reasoning or something, and create a data set for that. Definitely, they don't consider all the cases in which you have dependent facts, but there would be a starting point to looking to evaluating such methods.
Makes sense. Thank you so much for the great talk.
Thank you.
Well, maybe one more quick question. If there aren't others who want to ask, I'll ask one more. The fact-based embeddings. I can think of some ways to try to learn those, but what I guess what are your current thoughts?
Yeah, so I've been sort of thinking about two different ways to do this. One is using registers or so, and whenever a document, whenever you have a related document, using an embedding for that document in the prompt, like as a register or a soft token in the beginning. Maybe once you train your language model, you can freeze your language model and just train these registers for the document and learn facts that way. That's one thing I'm trying to do. The other would be using some sort of mixture of experts, fixed routing model, where you're able to route different topics or different facts through different parameters in the language model. But these are very vague, high-level thoughts. I don't exactly know how to do it.
Got it. Okay, thanks. And that's it's very different from how I was thinking about the problem. So, yeah.
I'd be curious to hear what you were thinking.
Yeah, right. Hopefully, we'll get a chance to talk more about that. Any other? Is there one more quick question from anyone, or? Looks like no. Okay, we should wrap up. But thanks very much, Varsha, for the great talk.
Thank you.